much time to focus on AP Stat. Yes. All right, good. So let's start Unit 8. We'll see how far we get today, how long we last. Okay. So Unit 8 is very different from the units we've been doing up to this point. It's all about linear regression. Do you guys remember from your algebra-based classes, like scatter plots and regression lines, that sort of thing?
Faintly.
Faintly. Do you remember y equals mx plus b?
Yes.
Slope intercept, okay? Totally different way of doing it, but that's like what it's based on. All right, so don't get scared. We're not like going back to algebra, but that's where it comes from. So we're going to look at having two variables, an x and a y. Your dependent variable is the y. Sometimes that's called the response variable. I'm writing really small. And then your x variable is the independent variable, and that's sometimes called the explanatory. So you're trying to predict y values when you're given x values. It's basically what this unit is all about. Yeah, go ahead. To do this, you'll always have two variables, and both of them are always going to be quantitative, the numeric type of variable. So I'm going to use that vocab word for a while. And all of this starts with a scatter plot. So we look at a scatter plot and we can describe the relationship. Your options are strong or weak, and you can tell me if it's positive or negative. And then if there happens to be a shape going on in there, we can talk about that. So let me draw just a couple of pictures for you here. So here's my scatter plot. If we're just talking strength and direction, I know that's kind of small, guys. So just strength and direction. Do you think that is a strong or weak scatter plot? Strong, yeah. It's pretty close to being in a line, right? That means it's a strong relationship. Do you think it's a positive or a negative? Negative. Why negative?
Negative.
Okay. Yeah, the slope is negative, right? Yes. You're like, maybe. So that is a strong negative scatter plot. So let's draw another one here. What do you think that one is? Weak? It's weaker. Yeah, definitely we'll call that weak. Positive or negative?
Negative.
Yeah, it's still going downhill. As it gets weaker, sometimes it's hard to tell if it's positive or negative, like if it's just this big cloud of dots. I don't know. But, so if there's just like no correlation between, yes, it can be like just no. But this would be considered weak and negative. So let's do, you can probably guess what else I'm going to draw. What do we think that one is? Strong positive. All right, and what about that one? Weak positive. So I'll sketch these shapes for you too, what you might see in your scatter plot. Most of what we're going to deal with, especially in this unit, is linear. And that's kind of what I've been drawing. It's not going to be a perfect line, but it should follow a linear shape. Parabolic, that looks like a parabola. So that could be a parabolic shape. It could also be the other direction. Exponential, we know what an exponential graph looks like. Exponential growth. And then your logarithmic. It's got a curve that levels out. I drew that for you. Again, what we're going to look at in this unit, you're going to be dealing with the linear. Oh, and I guess I say that in the next part. We're going to focus on linear regression, okay? So one of the most important things to remember is that just because it looks like two variables have a relationship, that's not a cause-effect relationship. You can call it an association, but not causation, okay?
Can you say that one more time?
Yeah, sure. So like, let's say, I don't know, let's think of two weird things we could measure. Number of times, I'm making this up completely, okay? Number of times tardy. Servings of cheese eaten. So let's say your scatter plot looks like this. Do we think that how often someone is tardy is caused by the amount of cheese they've eaten? No, there's some sort of weird association going on here, but it's not necessarily that eating cheese makes you tardy, okay? That's the difference there. So, and sometimes that's hard because it will look very much like one causes the other, but you can't state that. It's just an association between those two variables. All right, let's turn the page, guys. All right, so we're going to talk about the R correlation coefficient. It's this numerical number that you'll be given that tells you about the relationship between the two variables. It determines strength and direction. So from this R value, you can tell strong, weak, positive, negative, all of that. So determines strength and direction. There are also no units on R. So like the R value is never going to be like, I don't know, inches, degrees, anything like that. Like it's just a numerical value and that's it. It's always some value between -1 and 1. And the other sort of interesting thing is it doesn't change even if we change units. So let's say with our cheese example, even if we started measuring cheese in ounces and then we changed to grams. Changing that won't change the R value of the relationship between your two variables. Okay, so you don't have to worry about that changing even if you change your units. All right, and then your R value there, I think this part makes sense. This is pretty easy. If R is positive, that's telling you the slope of your regression line is positive, so you know you have a positive association going on. If R is negative, negative slope, easy enough. And then as far as the strength of the R value, the closer your R is to 1, so the absolute value of it, the closer it is to 1, the stronger the linear correlation is. If R is 0, you have no linear correlation. That'd be like just the cloud of dots. If it's equal to 1 or -1, your data formed a perfect line. If you're using real world data, super unlikely that you're going to see an R value of 1 or -1. Okay, the R squared coefficient, this, you find it by literally taking R and squaring it, okay? Like numerically, that's how the two are related. There's nothing weird there. But it tells us something a little different. It tells us the percent change in the response variable that can be explained by the change in the explanatory variable. I know that sounds weird with the wording. You will have to explain this as like part of a free response answer. It'll say, tell me what, you know, the R squared value means. And so when we get to some example problems, I'll show you just, it's formulaic how you plug it in to this part. You just have to put your context in. So remember the response variable, that's your Y variable, and the explanatory is the X. So it's talking about how much change in Y can be explained by X. The last two bullet points there, these are just make sense numerically. If you squared the R value, you're no longer going to have negative answers. So the R squared value is always between 0 and 1. And if your R squared is small, that means there's minimum association. If your R squared is small, it's because your R was small to start with. So that's why there's very little association. All right, then the actual least squares regression line, LSRL. This is like your line of best fit that you may have done before. The way it's actually calculated is it minimizes the sum of the squared prediction errors. You're not going to have to figure that out by hand. Again, your calculator is going to do all of that. A fun note, looks real fun, I know, guys. Your least squares regression line will always have the average X, average Y coordinate in it. So X bar, Y bar, that coordinate is always in your least squared regression line. Least squares regression line. It sounds more complicated than it is, I promise.
You're like speaking English with the words together, like art computing.
You're like, that sounds familiar, but what? Yeah, it's okay. Promise we'll get there. So it's a little different than what you may have seen in algebra. In algebra, we always did like the y equals mx plus b. That's algebra. For ours, we're going to do, we've got some b naughts and some b sub 1s going on. We usually have a predicted y hat is equal to b sub 0 plus b sub 1 x. So why we feel the need to change the order and put the slope in the x second, I don't know. It's so it goes in order, b sub 0 and then b sub 1. It's the same thing as what you did in algebra, it's just the notation looks different. So this one is the slope, and this one is your y-intercept. And that y hat, that's predicted y. Before we get too far into the regression line, let's practice a couple things with our R value. So let me just draw, if you want to draw these, you can. You certainly do not have to. I'm going to make like a little matching thing for you here.
Where do you recommend them be provided?
That's a great question. I don't know, you can do it on the back of the assignment sheet, that first page that's stapled there. I'm going to draw 4 different scatter plots for you. And then you get to match the R value. So try to match like 1, 2, 3, 4. You're going to match A, B, C, and D to that. So guys, try to do that. Talk to your neighbor, see if you agree, and then we'll go through. If you don't have a neighbor, find a neighbor.
I'm actually for D. And then B with 3 R. And then 2 with A.
That's why, like, it looks like, oh, fairly safe, but you need to actually try to match them up and be like, wait, do I get it or do I not get it? Because kind of can all float up here and then you're like, oh no, I don't understand. I know, it's part of it is my drawing skills. Yes, that is helpful.
Oh, this the latest?
Yeah.
It's supposed to be the straighter line of the.
Then D,
What do you say? Straighter?
I'll add a few more. I would say not. How about now?
Which one?
Okay. You're welcome. I know, I should have made them like 0.35 and 0.9 instead of 0.8 and 0.9, but. All right, guys, we think we got them? Okay, what do you think number 1 is? C, yes. I agree. 1 is C. All right, what about 2? A, yeah, 2 and 3 were kind of similar. What do you think 3 is? D is in dog, yes. So 4, did we get B? Okay. Now, obviously, hand drawn by me, not exactly perfect representations, but are we seeing, you know, the positive negative helps narrow it down, and then like just how closely it is to fitting on a line. Okay. All right. Does it make sense now, though?
Yeah.
Okay. Yeah, just think reading left to right. Which way am I going? All right, guys, so now this is talking a little bit more about like the regression equation, the line of best fit here. This is just a comparison for you of this is what you saw in algebra, and now over here is what we're seeing in stat. Okay. So the x we used to call the independent variable, now it's the explanatory variable. There's that equation you can see looks a little different. Slope went from being m to b sub 1, and your y-intercept went from b to b sub 0. Okay. Remember that with the hat, like y hat, that's predicted y value. These next two things, the interpretation of slope and interpretation of the y-intercept, these are important. You will absolutely have to answer these in questions. You'll be given all the information. They'll tell you the slope is, you know, 2.3. And then in the context of the problem, you have to say what that means. So you can use the word the average or the predicted change in your y variable. Question? Sure. I may or may not be able to answer.
So is this fine?
Oh, putting them in the chart, yes.
This is technically
Oh, okay. I don't think that should be
okay.
yeah. All right, and so again, it's wording of this, and you'll have to put it in context. So the average or predicted change in your y variable when the explanatory variable increases by 1 unit, because we're talking slope, so we want to make sure, think about slope, it's change in y over change in x, right? So if your denominator, your x changes by just 1 unit, like that's sort of the increments we're going by in slope, what is happening to the y value? It gets easier when we actually have a problem that we're doing this in, okay? The context actually makes it simpler. So, and then the interpretation of the y-intercept, it's the predicted value of your y when the x is 0, okay? Which you know that from algebra, right? The y-intercept, that's what happens when x is 0. This is just talking about in the context of the problem. Most of the time, it will not make any sense. Like you'll say, oh, we predict that there's negative 200 something when we have 0 of whatever else we're talking about. And it won't make any sense at all. But you still write out that that's what the interpretation of y-intercept is. Thank you. Oh, I'll grab you. Okay, good. All right, have you guys heard interpolating and extrapolating before? Do you know what those words are? Okay. Kind of. It's making predictions, but outside of your like range of values that you're looking at. So both of these are talking about making predictions. Interpolation is when you make a prediction within the data set that you have. Like you have X values from 2 to 10, and you make a prediction for 7, okay? It's good to interpolate, that's fine. Your results should follow whatever pattern you're seeing. When you get to extrapolating, that's where it gets dangerous, okay? You're going outside those values. Like if you have values from 2 to 10 and you make a prediction for x equals 30, do you know that the trend you saw between 2 and 10 is going to continue all the way out to 30? No, you have no idea what's going to happen beyond the data that you collected. So anytime you extrapolate or do things outside of those values, it's a dangerous situation. Okay, so don't extrapolate. All right, and then we've got a residual. This one's going to come up a lot in this unit, guys. So it's the difference of what the actual response variable value is from the predicted response variable value. So actual y minus predicted y. This part, I think, I'm going to give you examples so that you can see it. Positive residuals and under prediction, and then negative residuals and over prediction. Let's think about it. Is there what? I'm sorry. Like an over or under prediction? No, not necessarily. It's just a statement of like, oh, that was an over prediction. So let's say our y is the actual age of someone. We'll say they're 25. Let's say our y hat, so our y hat is our predicted y. Let's say that's 23. To calculate the residual, remember that's actual minus predicted. So that'd be 25 minus 23. My residual is 2. Does that make sense how a positive residual was an under prediction? The 23 was, yeah. I think without those numbers, it's like, why does that work? Let's do it again with a different prediction. Let's say my y hat is 27. What's my residual for that going to be? Yeah, 25 minus 27, I'm going to get negative 2. Okay? A negative residual means you over-predicted. Okay? And when we get to our last example here, we'll actually look at calculating residuals. There's a whole residual plot we'll do, but not yet. Yeah. Extrapolation. So not usually, and usually, oh, you can just set it all there. I'll grab it. Thanks. Yes, that. There you go. Because usually you're going to have some sort of y value that you know. Because to calculate the residual, you need the actual and the predicted. So if you don't have, if you're way out extrapolating, you probably don't have the actual y value anyway. So usually just in the inverse. Okay, guys, let's keep going. How we doing? Hanging in there? Okay. All right, so influential points. You guys don't have AMSCO books, so let's ignore this page here. They do. There is an AMSCO for AP stuff. Kind of. It's got like lessons and practice problems, and at the end there's like 4 practice AP tests. 3 or 4, I don't remember exactly. Yeah, it's very useful. So if you're interested in getting an AMSCO, it's good. Like, it's several. They are. All right, guys, so influential. This is another one that I'm going to draw a picture for because I think it's hard to visualize without that. So let's say I'm going to draw my scatter plot. Pretty strong positive relationship. I'm going to draw, well, try to draw the same one twice. It won't be exact. Okay, so I've got my 2 scatter plots. Once you draw those, then I'll put in my points. All right, guys, let me draw 2 dots. I'm gonna put 1 dot here, and 1 dot way out here. If I think about my regression line, like my line of best fit, try to draw it in on both of them. Without the red dot, are you guys okay with those regression lines that I drew? Those make sense? Okay. Which red dot is going to have a bigger impact on where this regression line goes? The first one or the second one? The second one, yeah. You know, I say in here, think of it like a teeter-totter. When you're further out, it's like physics. You have more force that you can apply here. So this red dot being out here is going to cause this regression line, like the slope, to dramatically change to try to account for that one. Whereas this one, like, yeah, it's far away from the regression line, but like it doesn't fit the pattern. It might adjust it, you know, something like that. It's not going to dramatically change what your regression line looks like. Does that make sense to you guys? So it's got to be far out on the x-axis to be considered an influential point. So we're talking about influencing your regression line. Influencing means change the slope. Okay. The outlier part, we're going to come back to that when we actually do a scatter plot of our residuals and then a box plot of our residuals, all that stuff. Yeah. Not necessarily. Yeah, that's a good question. They could be. Yes. Yep. To actually calculate the outliers, does anybody remember the formulas we used way back in, like, I don't know, unit 1? The IQR, yes, you need the IQR, the interquartile range. What do we do with it?
Subtract the lowest value. Subtract the lowest value from the next one.
Close, yeah. So like Q1, the edge of your box, if you're like,
Someone hit my car.
oh, that sucks.
So they told me to like.
Okay, thanks. I'm sorry.
I'll put this in my car. That's the information.
Okay. Oh, do you want to grab a packet too, just so you have one?
Yeah, sure.
This guy's so much
Yeah.
Is it bad?
It's pretty sweet.
Yeah. The same accident.
Oh
Same
my.
Same
I
person?
did on the side.
Does that person not know what they're doing?
I saw
Back. Is this like a video game? Like,
Wait, didn't know.
Video was like they filmed mine and they got scared and they moved too fast. I parked in the trailers. It's not easy to park there. To be fair.
it's true.
I don't park.
Slow it down, man. That's rough. All right, so back to our outliers, guys. All right, so the low end, you start at Q1 and then you go 1.5 IQR below that. So Q1 minus 1.5 IQR to get the low outlier endpoint. And then to get the higher one, it's Q3 plus 1.5. Well, you know, because if you think about it, you remember what a box plot looks like. It's been a while. You know, this is your IQR here. And this is your Q1 and your Q3. So it makes sense to add to the Q3 to find, you know, the upper, and to subtract from the Q1 to find the lower. And again, we'll do all the residual stuff on your calculator when we actually get to an example where we have data values to plug in.
you get fish and it's horrible.
Where is that?
I don't know, but that's horrible.
It's gonna upset some kids. Yeah, definitely. So guys, some of the formulas from this unit that we're talking about are on your formula sheet. This B1 equals R times S sub Y over S sub X. We'll get into using that more later. But that is how you can find your slope. Again, we'll look at that a little more later. But usually you know 3 of the 4 values, and then you just have to algebraically solve for the 4th one. So this is one of the few units where you might use a teeny bit of algebra as we're going about it. Okay? And again, that's not, we don't have a page 49 and 50. So
You said that Cleveland was how you find slope.
yes, yes, B1 is slope. B sub 1. Yeah. Okay, guys, my goal today was to get through the first example, the jet ski example, and that's what's next. So we'll get through that and then we'll stop. Okay, so hang with me, power through one example. All right, we're talking about jet skis. So our jet skis, also known as personal watercrafts, PWCs, are they dangerous? We're going way back to the August 1997 issue of the Journal of the American Medical Association. What'd you say? Probably. The design of a jet ski has changed tremendously since 1997. So we'll go with the data they give us. So let's see. The study recorded the data on how many jet skis were in use and then the number of accidents related to their use for 5 years. This is what a computer printout looks like that you might be given. There's a lot of information in it. A lot of it you don't actually need. Yeah, that's what I'm going to help you figure out, like what in the world are these numbers and what do we use them for. So first, let's define what our X and Y variables are. Like, what is our explanatory? What is our response? All of that stuff. So, any guesses as to what our X and Y are? What are the 2 things we're talking about in this problem? Yeah, okay, what do you think? Okay.
Versus the, oh, okay, the number of injuries versus the number of deaths.
Yes, like how many are in use and then how many injuries come from those being used. So the X is the number of personal watercraft in use, so PWC in use. And then your Y is your accidents or injuries related to that. Does that make sense? Because we're saying then that there may be an association between how many are in use and how many accidents happen. Like the more personal watercraft that's in use, you would expect more accidents. Does that make sense? Your X and your Y value there? Yeah. No.
They said, like, the way that they set up the question, they like put the
Usually, yeah. The wording of the question is going to give you idea of, okay, which one am I going to make a prediction for? And which one might explain that prediction. And sometimes if you're stumped, like look farther down in the problem, there may be a section of it that says, predict how many accidents would happen if, and then you're like, oh, that's what I'm predicting. Okay, so read through the whole thing. Do you have another question, Matt?
You mostly just answer it. I can just see the practice.
Okay, yeah, and this is all, like, it's a lot of information on there right now, so. Okay, and remember our formula. I'm gonna write it above the box here. You know, we're used to y equals mx plus b. We now have y hat equals b sub 0 plus b sub 1 x. Okay, the b sub 0 and the b sub 1, those are given to you in this computer printout box of information. Would you agree that b sub 1 is a coefficient on your x value? Right? Like, isn't that a coefficient? You're going, oh gosh, back to algebra. Yes, that is a coefficient. That's what, okay, good. That's what this is talking about here. So coefficients, we probably want these two numbers. And then we have to figure out which one goes where. Well, one of them is a constant, and the other one says the coefficient on personal watercraft. So, okay, this is another place where you can help figure out what is x and what is y. You're like, what? It's a lot of info. Okay, so let's write our regression equation. I'm going to write it two ways here. I'm going to say y hat equals, okay, b sub 0 is your y-intercept. It is a constant. So what number up here is our y-intercept? Yes, negative 2,745. All right, I'm going to say plus.
So is the b sub 0 always the constant number?
Yes. Yep. So yeah, I'm going to write it next to it for you. B sub 0, and then B sub 1 is going to be your coefficient on personal watercraft, because that's what the x represents. Okay, so we would have plus, and you don't have to write the whole thing. I would write 0.018 maybe. 0.018x. Now, sometimes you're going to need to write this with the context of what we're talking about, not just x's and y's. If you take the time to define the x and y, you don't have to. If you don't define it, then you're going to want to write your equation in words. So you're going to want to say predicted, I can spell on a Friday afternoon, personal watercraft accidents, that's what y hat is, equals negative 2,745 plus 0.018 times personal watercraft in use. Okay, so again, we defined them up above. Either define them or write your equation with words. Either way is fine. Are we okay on picking those numbers out of the computer printout? Okay. Maybe. Go back. The next two, let's do these out of order. Let's do what is the value of r squared first. What'd you say?
0.512.
Yeah, you guys see it right here? It says 91.2%. Your r squared is 0.912. Okay, so they will give you that value. You're not going to use the r squared adjusted. You're just going to use the r squared value there. Then let's go to the previous question. What is the value of r? If you know r squared, can you find r? Yes? What would we do? Take the square root. Okay. So what do you get for r? Do it as a decimal. Okay, I have 0.955 written down, but I may have rounded wrong.
No, it's
Is it? Okay. 0.955. Now, something to think about here, when you're taking the square root on your calculator, it's always going to give you the positive answer, right? Is r always positive? No. What is r related to? Yeah, it tells me, like, is it going this way or this way? What else tells me what a line is doing like this or this? The slope, maybe, right? Yeah? Okay, so the slope in this equation, was the slope positive or negative?
Positive.
Okay, so my R value should be positive. Okay, so I'm gonna make a little note off to the side for you. Positive because slope, which was your V sub 1, is positive. Questions so far? Any part of that you need me to go back through? Okay. Last three things here. We're going to interpret B sub 0, B sub 1, and the R squared. So first, B sub 0, remember that's the y-intercept. Okay, what was B sub 0 in my equation here? Negative 2,745. Okay, let me write the interpretation and then see if it makes sense to you guys, okay? So the way we state this, we'd say we would predict that when 0 PWCs, the personal watercraft, are in use, so that's the X's, when X is 0, there would be negative 2,745 injuries or accidents, whichever way, from personal watercraft. Yeah, remember how I said the y-intercept interpretation usually makes very little sense? This is what I'm talking about. Yeah, it's good. We're just waiting for them to happen now. We've got a backlog. So, yeah, those are fixed. So even when it doesn't make any sense, that's how you interpret it. Okay, you're telling me what happens when X is 0, what is the Y value in the context of the problem.
So, like, is this how, like, the problem
Usually these have like a variety of questions, like sections to the questions. Kind of, yeah. It's not like your hypothesis test. You know, you won't have that sort of conclusion happening. And sometimes I'll give it to you in a computer printout form like this. And other times you'll actually have lists of data to put in, and then you'll calculate what all of these different values are. That's the example we're saving for next time. Feels right to save that. Okay, so B sub 1. What is B sub 1? Slope. Good. Okay, we're going to interpret the slope. All right, so our wording. The average increase. And I'm saying increase because slope was positive. If slope's negative, you're not going to say increase. Decrease. Yep. So the average increase in personal watercraft, either injuries or accidents, whatever you want to say here, when personal watercraft use increases by 1 jet ski is 0.018 injuries or accidents. Jot it down and then I'll explain. All right, guys, so remember slope, back to your basic algebra slope, change in y over change in x. So we're saying x as our denominator, that's the personal watercraft in use. So if we increase that x value by 1, we put one more jet ski out there, we're watching the snow, guys. I look up and everyone's just staring at the I mean, really, it is very fun. I'm excited. I don't know. I can't see that far. No, not yet? Okay. I know it oddly warmed up a bit today. I know, it was very cool. Okay, so back to slope, guys. So if we increase that x, personal watercrafts, by one more jet ski, we're saying that's going to make 0.018 injuries happen. Okay, like if we increased it by 10 jet skis, that'd be 0.18 injuries. Like, does that make sense? You're just talking about the ratio there. And you always do it with the x variable increasing by 1, because then you can use whatever the exact slope value is.
Or is that like a simple algebra set that's a corresponding with each jet ski is responsible for that many x?
Mm-hmm. Yep. There's that association. Yes. Okay. All right, we doing okay? Does that one make sense? Okay. Not can you write it on your own yet, but are you getting what I'm saying? Okay. Yes. All right, and then the r squared value. This is talking about what gets explained here. So about 91.2%, that was the r squared value of the change in personal watercraft accidents or injuries, sorry that I'm switching, can be explained by the number of personal watercraft in use.
What is it? Like how it's something like one slope? What does that look like?
So that is talking about the association between these two variables. So we aren't going to say like number of watercraft in use causes this many accidents, but we can say, hey, we're noticing this trend that there's a very strong connection between how many are in use and how many accidents happen, because our r squared and our r value were pretty high here. So like 91.2% of this being explained by it, that's a pretty strong correlation between the two variables. Does that make sense?
So it's kind of like correlation.
Yes, that's exactly what it's talking about. You have the association between the two variables. And it's saying what percent can be explained by what. Are we doing okay with, like, it's a lot of x and y, like y can be explained by x, that sort of thing. Are we doing okay with that? The wording in this one especially, a lot of it is going to stay exactly the same. You would say about, and then fill in your percentage of the change in whatever your y value, y variable was, can be explained by your x. Okay, so you just fill in the context with whatever your problem is talking about. So we talked about, let me go back to it, I don't know if it's here. So you usually talked about R in your algebra classes, the correlation coefficient, and then R squared, you literally are squaring the R value, and that's what that's coming out to, and it's by squaring it, we're now talking about what percent can be explained by it. But it's very much connected to how strong the correlation is between the two variables.
This is
Does
like,
that help?
I'll watch.
Okay, it's the first part. Yeah, it's tough jumping in.
are you able to quickly just go back to the?
Oh, sure.
It's the, like,
I think it was here. Oh no, hold on.
there we go.
There we go.
Thank you, Mr. Lee.
You're welcome. Have a good weekend.